Should I start?
In a minute still,
Okay.
I see that one participant has a problem joining.
Okay.
So okay. Hello everyone. Welcome to the second lecture of Shayan, Oveis, Gharan, and continuation of properties of real stable polynomials. So please,
Okay.
Shayan.
Thanks. Hello, everybody. Let me, before I get to the topic of this lecture, I just wanted to show an example for the last lecture. The last lemma we said in the last lecture. So remember, we were talking about a random spanning tree distribution. So let's say, I just want to show you one example just to remind you what we talked about. So let's say we have a graph G, and in this simple case, let's say my graph is a cycle of length 4. It has 4 edges. Let's give names to these 4 edges. Let's call them E1, E2, E3, and E4. Then you can look at the spanning tree distribution, like the generating polynomial of all the spanning trees, or of uniform distribution over spanning trees. It's a very simple polynomial. In this case, it's Z1. Let's call it Z1, Z2, Z3, plus Z2, Z3, Z4, plus Z3, Z4, Z1, plus Z4, Z1, Z2. Okay, so that's the generating polynomial of all spanning trees. You can divide by 1/4 if you want to make it a distribution, but it doesn't change anything about the structure of the roots. So this is basically G mu. If mu is a uniform distribution over spanning trees, this is the polynomial. Now, the last lecture I said, let's pick some set F. So let's say my set F of edges is E1 and E2. Sorry, E1 and E3. Let's call it E1 and E3. And I want to look at the distribution, basically project mu onto F. So if you project mu onto F, you see the following. The probability that a tree sampled from this mu intersection F is 0 is 0. You always get at least one edge in this set F. The probability that it is equal to 1 is, let's see, yeah, it's basically 1/2. So there are 2 cases that you get exactly one edge in the set F. One is this one, and one is this one. So in these 2 cases, you get exactly one edge, and the other 2 cases, you get exactly 2 edges. So you also get the probability that T intersection F equal to is 1/2. And it cannot be bigger than 2. Now, what I said in the last lecture is that you can write this distribution as a sum of Bernoullis. So what would be your Bernoullis here? You would have 2 Bernoullis, B1 and B2. B1 would have success probability equal to 1, and B2 would have success probability equal to 1/2. Now you can see that the basically probability that B1 plus B2 equal to I is exactly the same as the probability that T intersection F equal to I for any I. Okay, so I wrote this distribution projected on the edges as sum of Bernoullis. And the other thing I wanted to note is that this 1/2, this 1 and 1/2 I found for success probabilities has nothing to do with, say, for example, the probability of edge E1. The probability of edge E1 is 3/4. So this 1 and 1/2 just comes out of the roots of this real root polynomial that you would get. Okay, there is no question. I'll continue this lecture. I mean, switch to the second lecture material. Okay, so now I want to tell you more about closure properties of these real estate polynomials. So in the last lecture, we saw some simple closure properties. Now, the point is you can try and see which operations preserve real stability and which operations do not. So Borsia and Brandon, who are pioneers of this field, actually proved a very sort of meta theorem, which characterizes all linear operators that preserve stability. So I'm not going to say the theorem in full generality, but I say, one of the main consequences of it. So let me define a notation. So let's say you have this operator T, which acts on polynomial. So what T does is that it maps polynomials with n variables to another polynomial with n variable. And how does it act? I want to think of T as a differential operator. So I can write T as follows: a summation of all alpha and beta in z to the let's say 0 to the n of z to the alpha, or partial to the beta, c of alpha comma beta. So what does this mean? So I said in the last lecture, whenever I write z to the alpha, or I talked about z to the s for a set s, but for a vector, when I write z to the alpha, I really mean product of zi to the alpha. Okay, and alpha and betas are just non-negative integers here. So that's what I mean. What about partial to the beta? Here I mean product of partial zi to the beta I. So you differentiate zi beta I many times. And c of alpha comma beta is just a coefficient of this term. Okay, so this is a fairly general set of differential operators. For example, you can have 1 minus z1 partial z2. You can have, I don't know, partial z1 squared. You can have 1 plus partial z1 minus partial z2 squared, and so on. So these are like some examples of objects you can, of operators you can characterize this way. This is a very general class. You can essentially sort of model or write any linear operators as acting on polynomials, as long as a linear operator acting on polynomials of bounded degree. You can reformulate it in this language. But okay, let me just say the theorem of Borsia and Brandon in this language. So now, given T, so I need a definition. So given T, define f of T. So f of T is a polynomial in 2n variables, z1 up to zn, and w1 up to wn. And it is defined as follows: f of T is equal to summation of c of alpha comma beta, z to the alpha, minus w to the beta. And alpha and beta are in non-negative integers. Okay, so what did I do? Basically, this f of t is very similar to t, except that I substitute the differential operators with this new variable minus, with negative of this new variable w. Okay, now here is the main theorem of Borsia and Brandon. T is a stability preserver operator. Meaning that it maps real stable polynomials to real stable if and only if f of t is real stable. Remember, real stable as a polynomial on two variables, as a polynomial on 2n variables. Okay, so let me show you some examples. So let's look at partial z1 squared, for example. Then f of this would be minus W1 squared, and that's a real estate polynomial, so this is okay. Another example is I said 1 minus Z1 partial Z2. This would map to 1 minus Z1 times minus W2, which is equal to 1 plus Z1 W2. In the last lecture, we saw that this polynomial is not real stable. So this one is not. However, if I had 1 plus, sorry, 1 second. Yeah. So yeah, another one is say 1 plus partial Z1. So this one is maps to 1 minus W1. This one is a stability preserve, and so on. Okay. So let me also say one more example. If you look at 1 plus Z1 partial Z2, for example, then this would, f of this would be 1 minus Z1 W2, and this is real stable. So this is a stability preserve. Okay, so this plus here matters a lot. If it's a plus, it's okay. If it's a minus, it's not okay. Good. And also one other thing I want you to notice is that this is a characterization. So it says that if a polynomial does not satisfy this, it's not a stability preserve. Okay, so for example, like if you want to see a non-example, for example, 1 plus partial Z1 partial Z2 is not a stability preserver if you plug into this theorem. So what that means is that there must be a real estate polynomial that if you plug it in, it doesn't pop out a real estate polynomial. So what is that polynomial? Or what is an example of that polynomial? If you plug in Z1, Z2 itself, Z1, Z2, this is stable. And if you apply this operator, you would get Z1, Z2 plus 1. And this one is not real stable. So what you get is that this operator is not a stability preserver. Okay. Any question? Okay. Now, I want to show you some nice application of this. So there is this operator called map. It stands for multi-affine part. What does it do? Basically, given a polynomial, it will zero out any monomial which has a square and only keeps monomial which are square free, or the multi-affine part of a polynomial. So keeps multi-affine part of a polynomial. Okay. So like for example, if you apply map to, let's say, 1 plus Z1 plus Z1 Z2 Z3 minus Z1 squared minus Z1 Z2, basically I would get 1 plus Z1 plus Z1 Z2 Z3 minus Z1 Z2. Okay, so I will zero out this term. Okay, now here is a simple claim that map is a stability preserver. Okay, how would you prove that? You want to prove it using this differential operator theorem that we talked about. So I want to write map as a differential operator. How would you write map as a differential operator? Here is a way to do it. You let's say I have this polynomial p on n variables. When I apply map to p, I can do the following. I can take the product of 1 plus zi prime partial zi. Okay, so what is zi prime? Zi prime is a new variable. Okay. Or in other words, a new set of, think of it as a new copy of this of zi. Okay, so I apply this, then I map zi to 0. So what does this operator does? Whenever it acts on a monomial, if the degree of zi in that monomial is not equal to 1, is more than 1, this operator maps that monomial to 0. Because first you differentiate with zi, you still have one more zi available because degree of zi is more than 1. And then when you set it to 0, that monomial will map to 0. If you apply it to a monomial which has no zi, it doesn't do anything. Just the one operator acts. The one part acts. So yeah, so if you think about it, basically what it does is that, sorry, so if you have a monomial which has degree 1 of zi, you basically first differentiate zi, and then you plug back in zi prime. So essentially, you're just renaming zi with zi prime. So the new polynomial will be basically the same as the original polynomial, where every variable is, where only the multi-affine parts remain, and in the multi-affine parts, every variable is substituted with its copy, with its new copy. Okay. So now, I've written map as a differential operator. Now I said above that this thing, this guy, is a stability preserver, and setting to 0 is also a stability preserver. So this whole thing is a stability preserver, and therefore I proved that map is a stability preserver. Any questions about this? So okay, so this map operator has had many applications. I'm not going to talk about it in this course, but there is, if you look at this nice proof of Caddison-Singer problem and related stuffs in 2013-14 by Marcus Pilman Srivastava, they basically use this and variants of this operator in their proof. So what I want to tell you now is a simple application of this multi-affine part operator. Okay, so simple application. There's a polynomial called the matching polynomial of a graph. So what is this polynomial? Given a graph G, the matching polynomial, let's call it mu of G. And let me talk about, okay, let's start. This is this polynomial. It's equal to summation of all matchings M in G. And these are all matching, not necessarily perfect matching, just all matching, minus 1 to the M, minus 1 to the number of edges in the matching M, product of, not product, T to the N minus 2M. Okay, so basically, the way you want to think about it is that the coefficients of this polynomial basically is a count of the number of matchings in the graph of different sizes, size 1, size 2, size 3, and so on. Okay, now there's a classical fact due to Gottzel in like 70s that this polynomial is real rooted for any graph. For any graph G, the matching polynomial is real rooted. Now, if you look at, I mean, I've read the proof of Gottzel. It's in his book. I've taught it. You need about one lecture to discuss how this is done. There is lots of machinery that you need to use. But the thing is, once you have this machinery of real stable polynomial, it's actually a one-line proof to show that matching polynomial is real rooted. In fact, we can prove something much stronger. So let me say multivariate matching polynomial. So what is the multivariate version? It's basically the same. You sum over all matchings m minus 1 to the m, product of zi, where I is not saturated in m. Okay. Now so what I'm going to show in a second is that this polynomial is real stable. And if I show that, I'm basically done, because you can just substitute zi with t by symmetrization. We said that real stable polynomials are closed under symmetrization. You would get back the matching polynomial. But this is a much stronger fact. This is sort of a multivariate generalization of Gotzel's theorem. Now, how do we prove this one? So there is a equivalently, I can prove this one equivalently. I prove mu g, let's call it mu g bar, to be this one, minus 1 to the m, product of zi, where I is saturated in m. Okay, equivalently, I can prove this one. Why? Because remember, we said that the real set polynomials are closed under inversion. If you just substitute zi with minus 1 over zi, you would basically switch between these two representations. These two sort of are the same up to this inversion operation, and real estate polynomials are closed under inversion. Okay, so you can prove either of the two are real stable, and that would be enough. Now, how do we prove this one? So here's the interesting thing. I start with this polynomial, product of 1 minus zi zj for I neighbor of j. Okay, so for every edge in the graph, I pick the 1 minus zi zj polynomial. That's a real stable polynomial. So this one is real stable. And we know that product of real stable polynomial is also real stable. So this polynomial I'm starting with is real stable. Then, here is the interesting thing. I claim that this mu bar is exactly the same as map of this polynomial. That's the interesting part. So why is that the case? Just think about opening up this, let's give it names, this polynomial, let's call it P. Think about this polynomial P, which have the product of 1 minus zi zj's for all edges of my graph. Think about opening up this P. You see there are lots of monomials. Now, here is the claim. The claim is that if a monomial corresponds to a matching, meaning that the zi zj terms that you get in that monomial correspond to edges which do not share endpoints, then your monomial will be multi-affine, will be square free. In other words, every monomial that you would have in P corresponds to a subgraph of my graph, and a degree of every variable is equal to the number of edges incident to a vertex in that subgraph. If the subgraph is a matching, the degree of every variable is either 0 or 1, and the monomial is square free. And what map does is basically only keeps the multi-affine part, which means that it only keeps the monomials which correspond to matchings. So when you apply map, you exactly get this mu bar. And now we know that mu, because map is a stability preserver, we know that mu bar is stable, and that says mu of G is stable, the multivariate version of the matching polynomial. And from that, we get that the matching polynomial itself is real rooted. Okay, so basically, I just wanted to show you one simple example of this framework. There are many applications in which one needs to show a given univariate polynomial is real rooted. That may be very complicated to begin with. You need to figure out some combinatorial property of your object to prove this. But often one method to establish such a statement is to start with a polynomial that you can prove is real stable, maybe using this model of all stable polynomials, or maybe using some product form or such and such. So you start with a polynomial which you know is real stable. You apply a number of stability preserver operators until you get to the polynomial that you're interested in. And until you get to this univariate polynomial that you're interested in, and because you kept applying a stability preserver operator, you would get that the final univariate polynomial is real stable and is real rooted. Any questions? Okay. So if there are no questions, I want to talk about now the second application of this machinery. I call it the Gurwitz machinery. This is a very simple, simple machinery. I hope I can prove it today, but it has a lot of application, a lot of generalization. You'll see one of the generalizations of it in the second homework, in the second assignment. Okay, so let me start with I can directly say the theorem and then say some applications of it. So here is a Gurwitz theorem. It's proved in 2006. So let P be a polynomial in n variables with non-negative coefficients. Okay, so this is, so far I haven't assumed non-negativity of coefficients. Here I want to assume that the coefficients are non-negative and that is real stable. Then we have this property. If you look at partial z1 up to partial zn of P evaluated at 0, you can sandwich it between the following quantities. Infimum of z positive, P of z over z1 up to zn, and e to the minus n times infimum of P of z over z1 up to z. So up to this error, you can approximate this quantity in the middle by this infimum. Okay. So let me try to parse it for you. So what is the thing in the middle? What am I doing? I am taking derivatives with respect to all variables, and then I set all of them to 0. So what is this quantity? It's exactly coefficient of z1 up to zn, monomial z1 up to zn. Okay. So what this theorem is doing, it says that give me a real estate polynomial. Let's say you have a polynomial, you know how to evaluate it, for example, but you're interested in a very specific coefficient. This theorem allows you to sort of approximate that specific coefficient by optimization problem. Okay, it turns out that this optimization problem can be turned into a convex program. I'm going to say it in a few minutes. So what this means is that given this polynomial P, you can approximate the coefficient of monomial Z1 up to Zn up to a e to the minus n factor. Okay. Now you can say, okay, who cares? What are some applications of it? Why should I be interested in the coefficient of Z1 up to Zn for a real estate polynomial? It turns out that it's very important. So let me show you some. Okay. So here's what I'm planning to do. First, I'll show you some applications of this theorem, and then I'll sketch the proof of it. Okay. So application 1 is permanent. Okay. Let's say, okay, so first let me remind you, if you don't know the definition of a permanent, let's say you have a matrix A in an n by n matrix A. Permanent of A is defined as follows: the sum over all permutation sigma, the product of AI sigma I. Okay, it's a product of all diagonals you can get over a matrix A. So that's a permanent. If matrix, another way to think about it is that if matrix A comes from a bipartite graph, weighted bipartite graph, permanent is the summation of the weights of all perfect matchings in that graph. Okay, let me show you one example. So let's say A is this matrix with coordinates, the 2 by 2 matrix with coordinates A, B, C, D. Then permanent of A is A times D plus B times C. Okay. Now I want to rewrite the permanent as a coefficient of Z1, Zn, Z1 up to Zn of a polynomial. So what polynomial I'm going to take? Here is the polynomial. I'm going to look at, think about a vector Z with coordinates Z1 up to Zn, multiply Z on the right by matrix A. This would give you another vector. Then take the product of the coordinates of that vector. So basically, let me define this thing. This is exactly equal to the product over all I equal 1 to n, then the sum over j of aij zj. So this guy, this is the product of ith row with z, and then I take that's basically the ith coordinate of the product vector. Now I'm taking the product of all coordinates of the product vector. So for example, for the matrix A I showed above, if you act on this vector Z1, Z2, let's say this new operator I'm defining, it's going to be A Z1 plus B Z2 times C Z1 plus D Z2. Okay. Now here is the claim. The claim is that if you look at this polynomial you would get from this operation, and you take partial Z1 up to partial Zn, and then set everything to 0, this is equal to permanent of A. Okay. You can check it in this simple example I showed here, AZ1 plus BZ2 times CZ1 plus DZ2. What is the coefficient of Z1, Z2 in this polynomial? The coefficient of Z1, Z2 is exactly AD plus BC. Okay, I'm not going to prove it formally, but more generally, this is true. If you pick any matrix A, whatever entries does it have, you can you would get the permanent of A by looking at coefficient of Z1 up to Zn of this polynomial. Okay, so in other words, okay, so what did we have showed again? So let me write it down. So we showed that for any matrix A, partial Z1 up to partial Zn of this polynomial Aij Zj evaluated at 0 is equal to permanent of A. Okay. Now, one thing to note is that this is real stable, because if, okay, so now, sorry, let me assume that A has non-negative coefficients. Then if A has non-negative coefficients, each linear term is each sort of sum is a linear function with non-negative coefficients, so it is real stable. Product of real stables are also real stable, so this is real stable as well. It also has non-negative coefficients. Now you apply the Gurwitz theorem I said above. You apply that theorem, you get that permanent of A is between infimum of, let's call this polynomial P. Let's call it P of A. Infimum of P of A over Z1 up to Zn, and e to the minus n infimum of P of A over Z1 up to Zn. Okay. Now, I haven't proved it yet, but I told you that this guy can be cast as a convex program, so you can optimize it. So this says that. So this says that the corollary for any A with non-negative coefficients, we can approximate permanent of A, sorry, A with non-negative entries, I meant. We can approximate permanent of A up to e to the minus n error, multiplicative error. Okay. Now you can think, okay, this is not so interesting. In fact, there are algorithms using Markov chain Monte Carlo method, which approximate the permanent up to 1 plus epsilon approximation. That's true. So this is less interesting, but the interesting fact about this theorem is that the algorithm that you get is a deterministic algorithm. Okay, so it's a very big open problem whether there is a deterministic algorithm for permanent which can get as close to 1 plus epsilon. The best that we know to this date is so this gives e to the minus n. At the time, this was that Gurwitz published his paper. This was the best that we knew. Now, further improving this theorem using other facts about real estate polynomials, after a long line of work, the best that we know, the best today for deterministic approximation of permanent, the best that we know today is a root 2 to the n approximation. So it's slightly better than e to the n. And okay, you may think that there is a long way to get to 1 plus epsilon. These are like exponential approximation, but there is this note that if you get 2 to the n to the epsilon approximation, you can boost it to 1 plus epsilon. Basically, if you can get sub-exponential approximation, you can boost it all the way to 1 plus epsilon. So the whole deal here is that whether using these machineries or maybe using more facts about real stable polynomials or more, I mean, the other thing to note is that the proof I'm going to tell you today basically is not graph theoretic at all. It's like it's purely algebraic. So maybe using facts about graphs, you can push this much further, get a sub-exponential approximation, and then go all the way to 1 plus x. Okay, so this is one of the big open problems in the field. It's very closely related to this question of whether P is equal to BPP. And permanent is one of fundamental examples for which there is a very good randomized algorithm, but there is no deterministic algorithm. Okay, so there is one other application of this. I'm not going to tell you about it. So second application of this theorem is a proof of van der Waerden conjecture. I've written it in the notes. It's basically a simple consequence of the fact that I've written here. Basically, I mean, if you haven't heard about it, van der Waerden conjecture says that I mean, it's proven now, but it says that the permanent of any doubly stochastic matrix is at least e to the minus n, or in fact, n factorial over n to the n. And using this machinery, you can prove that as well. Okay, so what I want to do now, first, I want to tell you how you can convexify that quantity. And then I'll tell you the proof of Gurvitz theorem, if there are no questions. Okay, so first let me tell you the convexification. So again, remember, I want to look at this infimum of P of Z1 up to Zn over Z1 up to Zn. I want to tell you this trick because it's going to be also useful in the next lecture example, next lecture context. So what is the proof? How would you make this into a convex program? You do a change of variables. You substitute Zi with e to the yi. The point is, because Zi's are positive, yi's are well defined. Yi's will be just real numbers. Then, so you do this substitution. So now the domain of yi's will be all reals. And you do one more thing. You also take the log of the objective function. So, so I want to look at, So when I look at infimum of y in Rn, P of e to the y1 up to e to the yn over y1 up to yn, log of it. Okay. So the point is, first of all, if instead of the actual objective function, I minimize the log, is the same thing, because log is a monotone function. So instead of minimizing P of z over z, I can minimize log of P of z over z. And now I claim that this is the same as this. Okay, I just did a change of variables. Now the bottom one, sorry, this should be e to the y1 times e to the y. Okay, good. So after a change of variable, this is exactly the same thing. Now I claim that the bottom one is a convex program. Let's see why it is. I claim that this function is convex in yi's, and the reason is that log of it is basically log of p of e of y1 up to e to the yn minus y1 minus y2 all the way to minus yn. So this guy is linear. This is fine. How about this one? The first term is a term which is sort of log sum exp. Okay, so it's a well-known fact in convex programming that if you have a function like this, a log of summation of, let's call it ai times e to the bi times y, for AI is positive, this is a convex function. It's called log sum exp. Log of sum of exponentials. Okay, so this is it's a well-known fact. It's very useful in many of the regularizers people use for machine learning applications, etc. Here we basically have the same thing. The thing is, by doing this change of variables, zi to e to the yi, you get exactly a log sum exp. AIs are positive because polynomial p has non-negative coefficients. So you get log sum exp. It's convex, and you can optimize the quantity. Any questions? Okay. So if there's no question, now I go to the proof of Gurwitz's theorem. So again, if you have forgot about it, let me rewrite it again. So I want to look at partial z1 up to partial zn of p. I want to say there's less than infimum of p over z1 up to zn and e to the minus n infimum of p over z1 up to z. Now there are two sides to this inequality. The right side is sort of the easy side, and the left side is the hard side. The right side holds for all polynomials as long as they have non-negative coefficients. And the left side uses real stability. Okay. Now let's start with the right side. How would you prove the right side? The point is p has non-negative coefficients, right? So I can write p as follows. I can write it as c of 1, 1, 1, 1 z1 up to zn plus, let's say, p prime. Okay, so what is this? This is the quantity I'm interested in. This is the coefficient of monomial z1 up to zn. And p prime is the rest of p. I don't care what the rest of p is. I can write p basically this way. Just separate out the monomial z1 up to zn from the rest of p. Now, when you divide this by z1 up to zn, you would get c1111, which is the quantity of my interest, plus p prime, basically the rest of p over z1 up to zn. Now, because p has non-negative coefficients, so does p prime. P prime has non-negative coefficients. I also assign non-negative values to these z's. Z's are positive. So this says that this whole quantity is always non-negative for whatever value of z I plug in. So this means that this is always bigger than or equal to c1111, the coefficient of z1 up to zn in p.
So, sorry, Shayan. Mateus has a question in the.
Okay.
Maybe he can unmute himself and pose it, or in the chat.
Okay. Is the lower bound achievable, or is there hope that we can substitute? Good. No, there is no hope to improve e to the minus n in this generic form, at least. The way that the lower bound is achieved is for p, you plug in basically e to the z1 times e to the z2 all the way to e to the zn. E as in the number e, okay? That is not really a polynomial, I should say. But basically, for many of these theorems, it gives you a tight example. So to turn e to the zi into a polynomial, you can just write a Taylor expansion of it and then approximated by the first few terms. But the more the better approximation you have, the closer you get to the e to the minus n. Okay. The thing is, if you like e to the zi and you approximate it, you get a real set polynomial, and this theorem is tight.
Thank you.
Mm-hmm. Good. So we proved the right side. Now let's prove the left side. Am I still sharing?
Yeah, it's working fine.
Okay, good. It's good. Okay, it's good. So now let me prove the left side. So which is the hard part of it. So let me say first that it's very important that you assume real stability. If you don't assume real stability, it doesn't work. So bad example. So I mean, again, notice for the proof of the right side, I didn't use real stability. Now for the left side, let's look at this polynomial p, which is not real stable, but it's z1 squared plus z2 squared. So this polynomial is not real stable. The coefficient of z1, z2 is 0. Okay. Now, if I divide this by z1, z2, I get z1 over z2 plus z2 over z1. And now infimum over z, positive of this quantity is 2. Okay. So in fact, you cannot even detect whether or not this quantity, the coefficient of z1 up to zn is 0 or not, if your polynomial is not real stable. Okay, so I'll say more about this, what's happening here, and what is special about real stable polynomial in this context. But for now, let's just try to prove this. So I want to prove again the left-hand side of this theorem, and I want to use an induction proof. Or inductive proof. Okay, so first I'm going to write the base case. So the base case is the degree 1. Is the polynomial in one variable. So let's say p, or let's call it f. F is a univariate polynomial. Let's call it f of t. Univariate real stable, in other words, real rooted polynomial. We said that univariate, real stable, and real rooted are the same with non-negative coefficients. Then infimum of f of t over t over t for t positive is at least 1 over e. 1 over e f prime of 0. Sorry, the other way around. Once again. Yeah, 1 over e should be it. This is at least this. Okay, so this is the univariate version. Let me not prove this now. Yeah, let me first show you how this is used. And then if you have time at the end of the lecture, I'll go back and prove this. So assume this for now, and I want to use it to prove Gurwitz's theorem. So, okay, so let's assume the base case. In fact, I'm going to use this fact twice, once in the base case, and second in the inductive step of my argument, okay? So let's say I have now this polynomial p with non-negative coefficients. I want to use induction. So let's define Q to be partial Zn of P, and then evaluate it at Zn equals 0. So Q really is a polynomial in n minus 1 variables, Z1 up to Zn minus 1. Okay. Now, I know that real stable polynomials are closed under differentiation and setting to real numbers. So Q is real stable. Real stable, it has non-negative coefficients. Therefore, I can apply my induction hypothesis to Q. So what would I get? What I would get is that I know that, so by IH, I know that partial Z1 up to partial Zn of Q, sorry, Zn minus 1 of Q at Zi is equal to 0 is at least e to the minus n minus 1 of Q over Z1 up to Zn minus 1. Okay. Let me let me say one more thing. So the left-hand side here is exactly equal to the object I'm interested in. Partial z1 up to partial zn of p evaluated at 0, right? Because q was itself a differentiation of a derivative of zn. Now I differentiate everything else. So this is equal to the left-hand side. So I want to relate the right-hand side here, which is e to the minus n minus 1 q over zi's. Sorry, this should be infimo of z positive. I want to relate the right-hand side to the right-hand side that I have in the theorem, okay? So how would I do that? So assume the infimum is achieved at z1 star all the way to zn minus 1 star. So I should say I'm cheating a little bit here because this is an infimum. It may not be achieved. So to really do the argument correctly, you have to do an epsilon delta analysis. I'm not going to do that. You can do it for yourself. Let's just say it is achieved at z1 star up to zn minus 1 star. So I just drop the inf and I put a star here. Okay. Good. Now define. Okay, let me now continue. So define f of zn to be q of z1 star up to zn minus 1 star, comma zn. Okay, so the point is f is again real stable and non-negative coefficients. Why? Because again, we plug in real numbers into Q, which is real stable, and the polynomial is closed under substituting with real numbers. So I again have a real stable polynomial, which is real rooted and non-negative coefficient. I can apply the base case again, or this fact about real rooted polynomials I wrote above again. So I know that 1 over e, this says that 1 over e infimum of f of zn over zn is less than or equal to f prime of 0. Okay, so I know this about this f that I just defined. So now let's continue. So let's call this right-hand side. So the right-hand side that I have above, this right-hand side here, I can rewrite it. So it was equal to e to the minus n minus 1 q over z1 star all the way to zn minus 1 star. Good. So this is what? This is really equal to e to the minus n minus 1 of f prime of 0 over z1 star up to zn minus 1 star. Right? Because q is really q is really partial sorry, wait a second. What am I? Wait. Partial zi. Oh, sorry, I made a mistake. F is not q of z1 star up to zn minus 1 star, comma zn. Wait, what am I doing? Q is, sorry. F is, let's see. F is P of that, sorry. F is P of z1 star up to zn minus 1 star, comma zn. Okay, sorry. F is P of z1 star up to zn minus 1 star comma zn, then f is real stable rerooted, you have that inequality. Now, the point is Q, by definition, Q was partial Zn evaluated at Zn equal to 0. So Q is exactly f prime of 0. So this is, so you get exactly equality here. And now I can put the inequality, say that this is at least e to the minus n minus 1 times 1 over e, f of Zn, infimum of Zn, f of Zn over Z1 star, Zn minus 1 star times Zn. So this is from what I wrote above about f. And now the last thing to notice is that to compare this with the right-hand side of Gurwitz, the right-hand side of Gurwitz is the same thing, except the infimum is over all zi's. So if I take also z1 star up to zn minus 1 star into the infimum, this can only decrease the right-hand side. So it's like you optimize twice. First, you optimize over z1 star up to zn minus 1 star, then you optimize over zn separately. But if you optimize over all of them together, you could get only something smaller. So you get, this is at least e to the minus n, p of z1 up to zn over z1 up to zn. Okay. So again, what I wanted to show you was that, so basically the thing to notice is that we're not using anything, oh, there are some questions. Good. Should it be P? Yeah, Q takes on. Yeah, sorry, I fixed that. Yeah, good. Thanks for the comments. Yeah, so I should have defined P of, F is P of Z1 star up to Zn minus 1 star comma Zn. So, so it should be clear now. So one thing to notice is that this class of proofs is fairly general. I only used, I mean, I haven't proved the base case yet, and I'm running out of time, but hopefully maybe we do it very quickly in the next lecture. The thing is, for the base case, the main property that you will use is that a univariate polynomial, a univariate real-rooted polynomial is log concave. If you take the log of it, is a concave function over non-negative reals. So this whole thing boils down to the fact that you start with P, you do a bunch of differentiation, a bunch of substitution, and the main thing you're using is that whenever you get in this process, whenever you get to a univariate polynomial, that polynomial is log concave. So this whole process, even though I proved it for real estate polynomial, you can do it for a much more general class of polynomials, which are called log concave polynomials, or a polynomials whose univariate restriction you get by differentiation or substitution with reals is log concave. So Gurwitz and others have managed to use this machinery for a large class of objects. For example, you can use this to estimate mixed volume of a bunch of polytopes, or mixed determinant of a bunch of vectors. If you don't know what that is, okay, I'm not going to get into it, but for example, the point is mixed volume, if you know about it, is a log concave function. So the whole machinery, and after differentiation and substitution, it is still log concave. So you can apply the same machinery over to that class of objects and estimate mixed volume of set of convex bodies up to e to the minus n factor. Yeah. So another thing I want to tell you is that, so in this theorem, we talked about, sorry, where is the statement of the theorem? Yeah, here. Here we talked about estimating the coefficient of Z1 up to Zn. Now, more generally, you can ask, what about coefficient of another monomial? What about something much more general? What if I want to know the sum of coefficient of Z1, Z2 plus the coefficient of Z4, Z5, Z6? You can ask all those questions, and so the exercise you're going to do is about a generalization of this theorem, which answers those type of questions. Like more generally, if you want to know something about some function of coefficients of P, in what settings, or can you answer such a question? Okay, I should say, okay, so let me say one last thing. So I should say that the base case uses a real rooted polynomial is log concave over a real rooted polynomial with non-negative coefficients. It's log concave over non-negative reals. Now, more generally, a polynomial P with non-negative coefficients that is real stable is log concave over non-negative reals as well. Okay, so I'm not going to prove this in this course. I mean, we don't have that much time, but you can learn about it. I've proved it in notes. You can read about it in the notes. And this fact itself has a number of applications. Basically, these machineries allow us to think about real estate polynomial as an object you throw into an optimization solver, to a convex programming solver, and solve your questions of interest. Like these because of these properties, there have been several applications of real estate polynomials in problems coming, say, out of economics, like optimizing or approximating Nash welfare problem and many other things I won't have time to talk about, but it basically gives you a different aspect of this machine. Okay, let me stop here.
Okay, thank you, Shayan, for beautiful talk, and I'm looking forward to continuation tomorrow. Just a note for the participants: we keep getting comments that the program is quite packed and that you guys don't have enough time to go through the exercises. So we fully understand that. We are now discussing it with the TAs, but still I think so one change we already made is we are not expecting you to submit any attempts for solutions 1 hour prior to the classes, just because there hasn't, I mean, it's completely fine if you just come to the class and maybe there you discuss with the TA and you show a solution to a particular problem. And so please do come to the exercise classes, with whatever you solved. So we will make arrangements so that it fits the program. So thank you, and I will see some of you in 4 hours, and there will so soon the web page will contain a Zoom link to this one session where we will go slowly through this random walks on expanders exercise from Subhash's course. Okay. Thank you, Shayan, again. Bye-bye, everyone.
Bye.